And here we are at the final episode of Redox in Unit 3. It's coming back in Unit 4, just so you know. But for the last video, we're going to look at one more example, and I just have one more redox process that I want to show you, and that is the redox flow battery. So this is one of those things that you don't necessarily need to know how it works, like by memorization, but you should be able to apply whatever you've learned to analyze it. The nice things about redox, and maybe you don't think it's a nice thing, but there is always a different design. There's always a new design, new innovation in the field. And redox flow battery is a very old technology, but it's experiencing a resurgence in the past few years because of the push to renewable energy. So any redox or batteries or rechargeable battery technology is being revised and updated so that you could use it to produce electricity to replace fossil fuel, which is, that's a good thing. So redox flow batteries are flow batteries in which, so you have the positive electrodes and negative electrodes reactants flow through the system and stay in solution. So the main difference between the redox flow battery and a regular rechargeable cell is that everything is in a solution in a redox flow battery, hence the name flow, like things flow. So it's not really suitable for portable devices, but it's really good if you want to take advantage of elements such as vanadium that has a lot of oxidation numbers but doesn't really precipitate like PbSO4. So if you want to take advantage of those elements and actually harvest the flow of electrons between versions of vanadium. So you can't use it for a portable device, but you could build a really big flow battery and use it to supply electricity for houses, which is, I think, is the application of flow batteries that are being looked at right now. So we're going to look at one example of a vanadium redox flow battery. So this is a diagram. Show the structure of a cell in a vanadium redox flow during discharge. So you could write that as voltage. The reactants are dissolved in an acidic solution and stored in large tanks and pumped through the cell. A polymer membrane allows movement of particular ion. So you have this here, is acidic. There should be H plus somewhere. I'm going to call this A and this B because they both carbon, so it's a bit hard to distinguish them. The discharge overall equation is this, so once again, you should be able to analyze the information given to write half equations for reduction, oxidation, cathode, anode, and flow of ions. So I'm just going to do this fairly quickly. You should be able to do this quickly as well. I would say one of these questions take 10 minutes tops. You need to be very good at finding oxidation number at this point in your chemistry career. If you are not, then you need to practice because you have about 20 seconds to do it per equation. All right, reduction, positive 5 to positive 4, so VO2 plus. Please take care of write the notation correctly. VO2 plus. Okay, so that's that. What am I doing? Yes, cohes, acidic condition, so I can use cohes, so I need to add H2O. And then we're going to add 2H plus to balance the hydrogen. Key elements already balanced. And then I'm going to need 1 electron because this size is 3 plus and that's 2 plus. Another way to know that you only need 1 electron is if you look at the change in oxidation number, it goes from positive 5 to positive 4, so that's 1 electron being added, and you only have 1 vanadium species in the reactant and product. Oh, look at this. Oh my god, I haven't seen this in a long time. This is, you've been missed easy equations that only requires electrons to be added. Do you really think I will give you this in the sack? Okay, cathode. So the cathode is A because that's connected to the VO2 plus. So cathode's A, anode's B. Flow of electrons, H plus crosses the membrane to go to A. Try to be very specific whenever you describe anything, especially if it's applied to a specific question. So don't just say H plus goes to the cathode. I want you to tell me what the cathode is. All right, so this is a diagram. This is a little video of what actually happens. So at the start, because this is discharge, at the start you're going to see two solutions. So I'm going to assume that the red one, this one, This one must be the reactant, so the red would be VO2 plus. If I got the order right, let's see what I do. And the blue is V2 plus. So we're gonna start the video. And this is discharge. Did I get it right? Yep, so electrons going into the VO2 plus. And you can see how the solution starts to change color, and that's because it's producing, so in the left chamber, it's producing VO2 plus. Let's try again. So the yellow, orange, the orange must be this. So you can see how the red solution is being replaced with the orange, yellow solution on this side, and this one is getting pale. I don't actually know what the color of V3 plus is, but I'm just gonna say it's pale blue, sky blue. We're gonna go. I was just talking about something else. Okay, I'm not gonna launch into that story because it will take forever. But one more time, you can see this is what happens. It's actually very easy. So the solutions produced, and notice how it start to get pumped into the storage tank on either side as well. So that's discharge, and that's why it's a flow battery. So as the products are being made, it's gonna go into the storage tank. Okay, describe feature of the cell that allows it to be rechargeable. I'm just gonna leave the solution here. Essentially, the products of discharge, which are VO2 plus and V3 plus, they are not solid, so they don't remain in contact with the electrodes all the time, but they are dissolving the electrolytes and they can be pumped into the electrolyte tanks and can be pumped back. So they have access to the electrodes when recharge happens. And you really want to make that point very clear that in this case, even though they are not solid, they don't stick onto the electrodes, they still can have access to the electrodes during recharge. And that's very important for a cell to be rechargeable. All right, let's do the opposite. You know what? You can do this yourself. You just reverse the equation. So I'm just going to write the answer and you can compare it with what you wrote. And just want to show you the recharge process. So you're going back. I don't think it starts yet. Was that me? Was it me sighing? I don't know why. Okay, so normally you use like a renewable energy strategy. What's the word? So this solar panel, for example, you can use it to recharge. And what you see here is that it's gonna go back eventually. I cannot believe that that was recorded. Why was I sighing? I can't remember because I recorded this video a few years ago. So okay, so you can see how it goes back to red and dark blue as it is being recharged, and there's the reverse flow of electrons. I think that's it. That's it. We're done. You have to do a few questions, but I am done talking for this week. Bye bye.